This is the fall 2018 offering of Deep Reinforcement Learning and Control course. I'm Katerina Frangiadaki, this is Tom Mitchell, and we'll be instructors of the course this semester. Let's start directly with some logistics. The grading of the course consists of 2 parts, 3 homework assignments and 1 final project. The project part has been, you pick a domain of your choice and you try to make progress, and then we would evaluate your novelty and performance. This semester, we decided not to follow that road. There will be 2 or 3 topics in which you are free to pick your favorite and try to make progress. So it's going to be like a small competition. Although this gives less freedom, we believe it's going to push you to really understand the material better, understand the algorithms, their limitations, how to generalize them, to generalize what is the limitations, and we'll discuss. And this project topics will come back again and again through the homework, so there's not going to be a surprise at the end for the project. We believe this is going to much help your learning experience. Do you have any questions on this? This is a big change from last semester. Okay. Resources. For those that do not have access to GPUs, we're arranging with Amazon. So we'll offer you some free hours on Amazon machines, and we will update you on this on Piazza. This should be starting from tomorrow or in the next 2 days. Okay? So the first homework will come out in 3 weeks, so you are okay for the next 3 weeks not having access to resources. Probably we will ask you which one of you have access, so that only those that do not have advisors with the GPU clusters will be offered these free resources. So the lecture will be recorded and will be available inside CMU. Many of you sent emails about this. The prerequisites. For those that have not taken the official courses listed on the website, do email us. As some of you have already emailed, we'll get back to you within this week and let you know. The important thing that has not been resolved is regarding time conflicts. Some of you have said, oh, I'm taking 2 courses, they overlap in time. Can I take this course, register for this course, and attend online? We haven't decided this yet. We'll decide this week and we'll let you know on Piazza about this. People can audit the course freely, no problem. I mean, there are many of seats. It's a very big auditorium. What is the goal of the course? The goal is, how do we build agents that can learn to act and accomplish goals in a changing dynamic environment, as opposed to programming agents to execute tasks in static environments, like this factory robot. Okay? And wonderful factory robots have been available for many decades now, and they're very useful. And they're relying on the fact that the environment in the factory will not change. So they don't have any sensory input. They just execute some pre-programmed behaviors. They don't need to sense because nothing is going to change. Okay? And motor control is important. Acting is important in the world. You may think that solving math problems is more important, but guess what? This is not the case. Because the human brain has evolved for hundreds of thousands of years to direct human motion. That's why we care about this motor control. And Daniel Wolpert and your science in Columbia University has a wonderful TED talk that you can watch that exactly makes this point, that the brain evolved not to think or to analyze emotions, but rather to control movement in the world. By the way, I'm making this clear because right now it's 2018. When we talk about actions, many of you, in particular in this audience, may think that we talk about the world of video games. All of us spend time there every day. We talk about acting in the physical world around us. Let me give you an example why I do believe that this statement is important. This is sea skirt. It's all over in the bottom of the sea. And they're tiny animals with a small nervous system, which as soon as they find a rock they like and they don't plan to move, they digest that nervous system. They digest their brain. Okay? And many people have parallelized this process with getting tenure in academia. You don't plan to move anymore, so productivity may drop. Okay, what are we going to learn? We're going to learn a mapping from observations to actions. What are observations? Observations, whatever we take as input from our sensors. Humans have a lot of sensors. Vision is a very basic one. In fact, 80% of the information we get through our eyes. We have also tactile sensing. We have audio. We have smell. Our computers right now arguably have much worse sensors, but whatever is available, we should exploit it. So this is how the input comes. And the output is what? Acting in the world. Okay? And because we care about achieving specific goals, the mapping should also condition in the particular goal you have in mind. So many times you will not see the goal being explicitly as input to this mapping. Why? Because, you know, RL has been linked to doing progress in video games. In video games, there is a single goal, win the game. As such, you don't need to input it as input on that function that you're learning. But to build agents that can act in the world, they have tons and tons of different goals, okay? So in general, we will seek this type of mappings, okay? Input and goal to desired actions. Now, many of you, since the prerequisite is also machine learning, you'll say, okay, great. Let's toss the human brain and put a deep feed-forward network, and let's learn the mapping from goal and observations to actions. Okay? In fact, the mapping from observations to actions can be quite complex. Much more complex than 30 or 100 feed-forward layers. You may have simulators, mental simulators, that will allow the agent to answer what-if questions. What if I move like this? What's going to happen? What if I move like this? And unrolling this model forward, you can see which action gets you closer to your goal. You need to generate hypotheses of how to act. You may want to retrieve relevant memories for relevant cases you had in the past and try to generalize them in the current situation. Okay? So this mapping can be quite complex. And now you're going to say, you know what? Look at me. I type in the keyboard. I don't even look at the keyboard. I'm pretty sure there's no hypothesis generation when I type in the keyboard. I do it so mechanically. It's so fast. And you're absolutely right. I want to tell you that there is a huge difference between this mapping can vary. Let's see here. Based on your expertise. When you are expert already, indeed, this mapping may just be, you know, few layers of a deep neural network. But when you are a novice, you will require all this model learning, hypothesis generation, test and check, etc. And you need to be able to balance your expertise to your ability to generalize. Does this make sense? So we don't just learn one policy and we're done. We want to have an agent that is constantly learning and updating his policy set as it occurs more and more goals to solve in the world. Okay? And we care about generalizing those policies in changing environments. Okay? We don't care to be expert in one world that if this world tiny little bit changes, everything breaks, which is what happens right now on RL, a reinforcement learning for video games. Okay, so this is the big challenge. 1 second. So we talked about learning to act. Each time we learn, we need to have some source of supervision. So what are the sources of supervision for learning to act that we'll explore in this course? The first is rewards. Rewards is sparse feedback from the environment whether our desired goal has been achieved. For example, did we win the game? Did we drive safely? Did we manage to get out of the maze? Etc. And the truth is that those rewards do not need to be extrinsic to the agent and very difficult and far away in the future. In fact, these are fantastic learners, extremely fast, extremely self-supervised, which generate constantly goals for themselves. Can I make this noise again? Can I get that visual? Can I pick up the little toy in front of me? Okay? And this allows you to constantly explore without any extrinsic supervision from their parents. So those rewards are not only extrinsic to us, but also intrinsic to the curiosity of the agent. All right? Now, I want to give you a specific example of behavior and so that we analyze the different forms of supervision, the advantages and disadvantages of each. This is high jump. Does anybody recognize the two different types of high jump? Do you know the names of those? Well, I have the names. Well, the first is Caesars, is what was developed in Eastern Europe up till 1950s, and here is the Forsberry flow, developed in Oregon State University by Dick Forsberry. Okay? So what Forsberry did is he took advantage of the much soft landing material, which was not available earlier, and then completely changed the optimal, let's say, behavior for high jump from the scissors to this back flop. That took quite a long time to discover. Yet, as soon as the inventor showed it to the athletes and won the Olympic Games around 1969, then athletes around the world were very fast to fine-tune and improve quite a bit on his technique. Okay? So learning from rewards is difficult, but learning from demonstrations is easier. Okay? So as you saw, it took years to come up with a completely different strategy, but it took much smaller time to perfectionate the strategy once it was demonstrated. Now, my question is, once you go to a coach and you ask him, teach me how to jump high, how will the coach assist you? How will he supervise you towards this process? If it's for rewards, it will tell you, okay, do it thousands of times, see which way you go higher, and improve on your own. A better coach would say, don't worry, I'm going to show it to you, and he's going to be jumping himself many times, and he'll say, okay, are you watching now? Do you see how I'm doing it? Try to do it as well. And an even better coach will give you specifications of optimal behavior. He will tell you, okay, this is how your velocity should be, this is when you should place your weight from one foot to the next, that's how you should time yourself, etc. And this is the most common sense supervision that humans use from each other. We constantly program each other in natural language. However, this has not been successful so far in reinforcement learning simply because language grounding has not made enough progress yet so that we can use it as a viable source of supervision. But we will touch on this in this course. Do you have any questions so far on these forms of supervision? All right, so why learning to act is different than other machine learning paradigms? For example, my favorite one, learning to detect objects and images. Answers? Why learning to act is different? Why we need to have a separate course as opposed to putting it in general machine learning course? Yes?
Because with reinforcement learning, you're interacting with the environment rather than just like observing the environment.
Right, exactly. So this means, exactly because you're interacting, that the data you generate and you need to label are constantly changing based on your actions. So here is the agent, the brain, that interacts with the environment. You will see this loop many times. And as a response to its actions, the environment spits out different observations. So these observations, the images, are not IID, independent and identically distributed, but rather change as your policy is changing. Policy is the mapping from observations to actions. And now you're going to say, okay, sure, it's not IID, but why is this a problem? Why is this a problem? Why supervised learning breaks under this interaction of observation and action? Well, let's consider a very simple case to demonstrate the difficulty. This is a racing game. Imagine that you have used humans to tell you how to race a car inside a simulator. So you collected expert trajectories. What does expert trajectory means? That you can take them and strip them into this type of dataset. An image and a corresponding steering angle. Okay? And I'm asking you, I want you to learn to race this little car. So the first thing that comes in mind is, since you have this type of data, and since we've taken the prerequisite of machine learning. Yes? So I have the input, the images, and then I have a corresponding output. And then I want you to learn to race a car. So a new image scans, I want you to predict what to do. What are you going to do? You'll take these paired examples and train your favorite machine learning model using supervised learning, okay? Okay, our favorite model is deep nets nowadays. And the result will come out as the policy, the mapping from observations to actions. Now here's the problem. You'll go and apply now this policy in the racing game. And you will have done a pretty good job, but you will have a tiny little error with respect to the expert, which usually is not the case. But because this tiny little error, once you execute it in the, thank God, simulated environment, okay, will take you a little bit off-road. Now, this is not a big deal. The problem is that, in general, but exactly because in that new place where you ended up, an expert probably would have never ended up. You have no clue what to do in this new place. So once you try to fire your policy again, your error will be even larger and will take you even more off-road and even more off-road. And we call this compounding errors. So eventually you'll be completely off-road. So how can we, do you see the problem that comes from why supervised learning may not work once we learn the mapping from, and then we try to execute in the real world? Great. So let's discuss a very nice solution that was given a few years ago. And in the course, we will find a much sweeter solution soon to come, okay? We will not talk about this today, though. Okay, so you learned your policy. You apply your policy in your racing car game. Then you collect your new demonstrations. This is the new data, which potentially are images that your experts had not seen before. Okay, and you ask the experts to label those new images. So you query again your expert. Okay, you collect new data. Now what do? You add this new data to your previous data set. So that's why it's called dataset aggregator, DAGger. Okay, so now you have a larger data set, and you use this larger data set to train again your policy. And apply it again in the simulated game, and collect new data that you made mistakes. You query again your experts, and you iterate. Okay? And eventually, you will know exactly how not to go off-road. And this will push you back in. Of course, this assumes that you have available the expert to be able to query. Now, there is a much smarter solution given from NVIDIA in 2016, which they tried to learn exactly the same mapping for racing a car on a real road. So instead of having just a single camera, they had 3 cameras, left, center, and right. So they would use the left and right cameras simply just to do this augmentation of data. Once you see something a little bit of road, automatically they would point a steering wheel towards the center, okay, without asking any human. This is right, automatic, exactly because you know how your cameras are placed. And this worked really well and solved the compounding error problem. But of course, this is just for racing cars, right? The compounding error arrives in any type of policy you may want to learn. So we want a general solution to this, and will come later in the course. OK, great. So the first problem is that the data is not IID. The second is that the reward, okay, whether the goal of the behavior has been achieved, is far in the future. In supervised learning, the goal is closer, okay? So as a result, we have this what's called temporal credit assignment, which actions were good and which actions were bad, which actions were critical to lead us to the goal being achieved versus which actions did not matter. Now, I want you to make the following connection. Someone can say, wait a second, isn't the same also in object detection? People use extremely long neural networks. The rewards are after 100 layers that tell you whether you classified or not correctly the image or whether you detected the object. And you are supposed to decide the weights in all those neurons, which are many, many stops earlier in time, I would say. Isn't it a similar problem? You cannot have supervision of whatever neuron needs to do. Well, one difference is the following, that once you have these super long networks, because exactly you don't need to go through the environment, the errors, the grants can go backward. You can just use a chain rule, but you cannot differentiate through the environment. So it's much harder to propagate those later error signals, okay? I thought that was a nice connection we discussed with Deva Raman a couple of years ago. Okay, now here is the big problem. Actions take time to execute in the real world. And there is you just cannot afford to have that much interaction time. A baby can afford it because it's, I mean, the motors, I mean, it works 12 hours a day and is pretty, you know, his motor system is well developed and collects a lot of experience, let alone all the pre-training in his brain, in her brain. What can we do for our agents to get the same chance? Well, first of all, we can use simulators. And then we'll learn some policies and try to use sim to real transfer to transfer in the real world. Now, let me go back to this. But the problem is that this simulator not only needs to have photorealistic visuals, which I would say is pretty, I mean, we have wonderful movies right now. How to say, cinema does have fantastic photorealistic visuals. Getting realistic physics, though, in the simulator is pretty difficult right now, both for rigid bodies and, I mean, let alone non-rigid bodies, okay? We can get our robots to work 24/7. Right now, in the robotics paper, they're going to say, oh, I put the robot 50 minutes, I collected 2-3 trajectories, I fitted something, here is the result. 50 minutes is not enough. However, here in CMU, Abinov and Lerel let their robot work for 700 hours. This, in my opinion, was revolutionizing work. Why? Because first of all, you had to fight with the CMU safety rules that you are not, yes, you cannot leave the robot unsupervised during the night. So then somehow they said, oh, we supervise the robot so the graduate student would die there. Look, every day, but there was no supervision. So you had to go to bypass all these rules to allow the robot to play on its own and explore. Okay? Here is the robot exploring. Now, your question might be, how interesting things would you be able to explore a robot alone? The result is not super interesting things. You just push objects around, pretty much, right? You don't do anything interesting like putting A inside B, or maybe stacking, or this and that. So how can we combine self-exploration of our robotic agents with guiding them a little bit towards interesting parts of the state space? It's one open question, okay? Okay, so one solution is to make the robots work more, and the other is to just buy more robots. And this is what Google has done. They call the robot farm, have many agents jointly collecting examples and learning one common policy from examples that all those different arms collect, okay? I mean, as robots get cheaper and cheaper, potentially this type of framework may be more, easier to have also in academia. Now, my question is the following. If we had fantastic simulators with wonderful physics and wonderful visuals, and if we could, collect a lot of demonstration for humans, would manipulation still be a very difficult problem? Because what we saw in Emergent, for example, we brute forced the problem. We went out and said, okay, what are all the classes I care about? Here is a list of, let's say, 3,000 classes of objects. Let me send millions of examples to, crowdsourced workers and learn the mapping that I care about. Do you think that if we had these resources, we would be able to solve the problem? For example, of manipulation. Okay, so I'll give you my answer. So this is, please feel free to say your opinion. But my opinion is yes. Learning how the world works is so difficult, right? And coding it up in a simulator, if I was able to learn the simulator, that's it. That's the end. Then I can just adapt myself, self-train myself in that wonderful world, and I will be perfect. Okay, I mean, I would need some time, but we have resources. We can parallelize this exploration. I mean, humans had the chance of living for hundreds of thousands of years, but now we have the chance of parallelizing the exploration and adaptation of our algorithms. Okay, so that's the first chapter. So do you have any questions on this or any comments? It doesn't need to be questions. Yes.
Thanks for the introduction. I was wondering if you could slow down a bit.
Am I talking?
In your explanation, it was hard to grasp what's the meaning of intrinsics for rewards, policy, what's the differentiation between a policy and a plan, what's the meaning of an observation and mapping to an action.
All right, so first of all, so let me slow down while you're talking. These terms will be visited again in fact on Wednesday, but simply because you mentioned this, let me just say a few things. Observation is whatever comes from our sensors, whatever is input from our sensors. And we're able to observe from, for example, is the images from our cameras, or is the tactile signal from our tactile sensors, okay? Then the policy is the mapping from those observations to actions, okay? That's the policy. What intrinsic means is that you don't go to the baby and say, make sure you have a tower here by tomorrow, okay? You just let the baby, and the baby, from curiosity, this is what psychologists and neuroscientists suggest, that humans have this, they want to explore, and they're curious, and they want to learn to predict about the world. And they're guided simply by building good predictive models. And later in the course, we'll explore one work that the only reward that it has is to make its predictive model fail. I want to act so that the learned model I have built so far will fail. And as a result, they can solve a lot of Atari games. They never get feedback whether they succeeded in the Atari game or not. They just get feedback whether what they have done surprised them or not. And they show that this type of policy, a policy that is trying to make my learned model fail, correlates very well with succeeding in the Atari games. And by the way, to do that, they did not need to encode death on that Atari game. The agent would just die and go back in the beginning. But at some point, the agent learns not to die because it will have to run the whole game again, and it has seen it before, so the predictive model would be very good in predicting it. So you better not die if you want to surprise yourself. We will go know this in very, very much detail, okay? But because I do want this, first lecture to be exciting, but at the same time, not to go too much above our heads. Please do stop me if something is not clear, okay? Now, I'm not sure how many people understand what is a model. A model is a simple mapping of whatever I see, okay, my observations, and my actions to my future observations, okay? Right? This is exactly the step function in the physics simulator that take the current state of the world and the action of the agent, and they map it to a new state of the world, okay? Simulators know the model, okay? Video games, we know the model. When we're in the real world, we don't know the model, we need to learn it. And we'll come back to that point later. But please, yes? No, I'm done.
Okay. So like with automated learners, is there like a possibility of a kind of a deeper level transfer of knowledge beyond just demonstrating and creating new data? Like if you had two robot arms of different companies, and the first one picks up cylindrical items, and the second one picks up spherical items, is there like a way to combine them to make a whole?
I think your colleague is saying, learning from demonstration, you told us. However, it seems that the way you suggested that we learn from demonstrations is through what's called behavioral cloning. Let's just learn the mapping from those observations that the expert encountered to the actions that the expert chose, correct? The problem with this is that you can never generalize beyond what the expert has seen. If the expert manipulated this particular object, you will never learn to manipulate a different object. So that's exactly what's going to be one of the two topics, or maybe 3 or 4, of the project. How do we generalize demonstrations in manipulation? Because yes, there is some current research on learning from demonstrations, but potentially, exactly because this generalization is not strong, is very, very small, in terms of the interpolation of that the neural net can do, we will exactly ask the following question: how can you generalize beyond? Does this a little bit answer to what you said? No? Any other? Yes.
So you said one difference was supervised learning is that in supervised learning we can backprop through the entire model. If we have differentiable environments or simulators, can we do the same thing?
Yes, we can. And in fact, that's going to be one class of models that we'll explore. How can you learn neural recurrent models that you can totally unfold, take the rewards, and backprop? Yes. And that is an ongoing, and then you're going to say, okay, great, why don't we just learn a recurrent network done? But let me tell you, Because the question is, in what representation are you going to build this recurrent net? On the observations? It's very hard to predict the observations. What is the intermediate state on which you can build this recurrence? Okay, because look, in the observation now you cannot even see where my hand is. Okay, so the observations forget. Oh, how can we build this intermediate representation that the state will be remembered? Okay. Other questions? Yes. By the way, those questions that are not answered in the class very well, you should not worry about them. You can just post them on Piazza, and there we'll try to reply, and the TAs will reply, and there are going to be discussions. So, yes.
What's the difference between a policy and a model?
Right. So the policy, there's a huge difference. The policy is a mapping from observations and a goal to actions. A model is a mapping of actions and observations to future observations. A model can be unrolled in time. You can say, if I do this, I'm going to end up there, and if I do this, I'm going to end up there, and then you're alone in the future and try to see future consequences of your actions. And it has also been considered that a model can generalize better across domains, of course, depending on the representation that you build it on. While a policy is useful for a particular task, and once you switch task, you cannot use it anymore. Other questions? Yes.
How is the policy different from a plan? Are both of those the same?
So we didn't use the word plan so far. I think a plan is, we can think as an unrolling of the model forward. If I do this, what's going to happen next? Okay. I think what people differentiate is that a policy, usually when they mention to a policy, is a reactive mapping between the observations and the actions, where the plan may incorporate things like the model and look ahead and, more, as what we said earlier, right? More aside of reactive mapping. Mm-hmm. Shall we continue? Next, we will see some successes of learning to act so far. The first thing we'll discuss is about backgammon. Backgammon is a very old game. For example, 1,000 years older than chess. Now, everybody knows about Deep Blue, the program that beat Kasparov in chess in around 1996. Why we don't talk about chess and we talk about backgammon? What is the difference between backgammon and chess? Well, and how these two games were solved both inside IBM. Chess, branching factor of around 30 to 40. What is a branching factor? Given the current board configuration, what are the next possible board configurations? Okay. Now, backgammon, in the contrary, because you roll the dice, it has a much larger branch factor. As a result, tree search, essentially unfolding all possibilities forward, is prohibited in backgammon. Okay? Interestingly, chess, let me discuss about chess. Simply because the people that solve chess in IBM essentially come from CMU. They came from CMU. They started this project earlier. They built this small company called Deep Thought. This was acquired by IBM. Then it changed the name to Deep Blue. Okay? And their developer said, you know what? This program that solved chess is not exactly AI. It was simply a brute force solution. We tried to learn an evaluation function, essentially mapping the board position to how good it is, how likely it is to lead to success, simply by collecting lots of features and talking to many chess experts. Okay? Does this make sense? And in fact, a master of chess was part of the team, of the development team, and Kasparov had said, can I also see those games and those moves? And they said, no, you cannot. You cannot see. Now let's go back to backgammon. So we excluded, exhaustive search, which means, let me just unfold, see, based on the manually defined evaluation function, which action is better, and let's take that action. So how did Gerald Tesoro tried to solve backgammon in IBM. His first attempt, he called it neurogammon. Why neurogammon? Because it's a neural network that would take the board configuration and would map it to action. All right? Now, what do you think was the board configuration input look like? Do you think it was pixels? It was not, of course, pixels. It was features of the board position. It was an encoding of the board position, manual encoding, okay? And the neural network only had 80 hidden units. That's it, 80 units. Okay? So you take the board configuration and you map it through 80 units to an action. Okay? How it was trained? It was trained to mimic expert moves from 400 games. Who was the expert? Gerald himself. He played 400 games and told the computer, that's what you should do at this configuration, that's what you should do in this configuration. Now, what's the problem with this approach? The resulting neural network that was trained could never do, of course, better than Gerald himself. As a result, he achieved intermediate level human player performance. Okay, that's fine. Now, he didn't stop though, that's the thing. He went on and he did what is called a TD-gammon. TD-gammon is still a neurogammon in the sense that there is still a neural network that maps board configurations, this time not to actions, but rather to values. Okay? How good is this board configuration? Same thing was the case for chess. Now, what is the difference? The difference is the way this evaluation function was trained. In chess, we recruited many chess masters. In TD-gammon, we didn't recruit backgammon masters at all. We didn't have any supervision from experts. Rather, we let the computer play with itself. Okay? Here is the evaluation function. You take an encoding of the board and you try to predict to the probability of success. What exact algorithm was used is called temporal difference learning. What exactly does this mean? Essentially, you try to make the evaluation of the current board position closer to the evaluation of the future one. Eventually, the future will be what? The end of the game, you will know whether you succeeded or not. So this success or failure will propagate and inform the evaluation functions of the earlier board configurations. Does this make sense? Okay, great. So we have the evaluation function. How this was mapped? Well, there was a tiny, small look-ahead search. It was exhaustive search. You would try all the possible configurations. Remember, the branching factor is very big, so this search was only 2 steps. So each time, you would unfold 2 steps, see the branches, see if you know which, see the evaluations of the resulting board configurations, and try to propagate them forward in time. And we will look into this algorithm very much in detail in the 2-3 lectures from now. Okay. Now let's see. How many games do you think it had to play to get an informative evaluation function? 1,500,000 games. Okay, but Gerald did not participate in any of them. This is just the computer alone playing. This is great. As a result, it was almost beating the best player of its time. And then Gerald didn't stop. He said, I'm going to take the features from neurogammon, instead of starting from scratch, I'm going to pre-train. I'm going to pre-train to mimic expert moves, initialize from there, and then start playing. And then he was able to beat the backgammon champion of his time. Great. Nice. So, self-driving cars. Again, there is a CMU story behind learning to drive. This is Alvin, which is... So, by the way, are there any questions with the backgammon? Something that is not clear? Yes?
With an evaluation function, don't you still have to like do the whole branching factor thing when you need actually encoding of the action to
No, you don't need to encode the action exactly because the policy did not participate at all on that tree unfolding. That tree unfolding was extremely dumb. All possible cases, and then again for each resulting case in all possible cases, and then you look at the evaluation function of the resulting board configuration. So now I'm going to say, but these are not good. Sure, they're initialized from scratch. The network is initialized from scratch, so the evaluation function will be completely random in the beginning. But as you play and play and play, and you'll see that this resulting configuration is bad, then this will propagate forward in time to say, you know, that resulting configuration is also bad, or at least is worse than this other one. Okay? Does this make sense? You do not need to learn a policy at that case. Evaluation function, one neural network would do the job. We will see later there are other games where they were training two functions, one for policy and one for evaluating the board configuration. Okay? Other questions? Okay, self-driving cars. So, the Temporal in CMU in 1981 had the truck that could drive on its own. This truck, amazingly how, had 4 hidden units. This is pretty crazy. The input image was 30 by 30. He generated those images in simulation. Interestingly, generating those simulated images took much, much longer than training the network. You see, 30 by 32. Now what happened? He realized the problem of compounding errors that we talked earlier, and he did augmentation of his data. So if the lane would look this way, he would push it, push the steering wheel towards the road, and again, if it would go the other way, again, push it towards the road. Now the problem is the following. The capacity of this network is very, very tiny. So you cannot just train something in simulated images and deploy it. Once you open the trunk, you switch on the camera, and you see the surrounding, he had to fine-tune that network in the beginning using the expert moves of the driver. And once fine-tuning is done, then the driver will leave the wheel and the car would go. Okay? Makes sense? Let's see. Oh, here it is. So ideally, we would like to have some audio now, but it's okay. I switched it off. So now I'm going to say, since from 1989 we've been driving, why still the problem has not been solved? Because this is isolated drones in the middle of nowhere. There are no people, there are no other cars. You just need to follow the lane, okay? And, I mean, the sensing is very simple. You just need to keep track of the lanes of the road. However, once you go to urban centers, you need to keep track of the pedestrians, of the other cars, of the traffic lights, of the other traffic signs, okay? And the mapping from the input to what you need to do is way more complicated. Potentially, you need to take into account what this pedestrian is trying to do. How can I forecast his motion? How should I make the car behave so that it respects this pedestrian, okay? This is a difficult problem, okay? Because in the real world, we never take crazy actions to say, if I do this, what the pedestrian is going to do? And try to do unsafe, let's say, commands. So coming up with this cost function is difficult. Now, if the people in the company say, oh, how wave driving is solved, it's very easy, just follow the lane, sometimes bypass. However, once you go to traffic jams, it's extremely difficult. The car is going to freeze there forever, it's not going to move. Do you see? Because it doesn't know how to break the rules. Okay, so how do we teach the car what is a natural driving behavior for humans? Okay, I would say it is simpler to just talk to the car and say, hi, go now a little bit. Do you see? To guide it through, let's say, language. And language car may be extremely easy. Like, oh, make sure you keep that much distance from the front car. And in fact, there is a paper that did like this. It defined some affordances and tried to learn to drive through these affordances. An example that everybody knows is DeepMind. 2014 plus, they learned to play Atari games, okay, without any human input, simply by reinforcement learning. And that was important because they learned the mapping directly from pixels. Previous works had already learned to map the image to some intermediate representation. They showed that this mapping from pixels all the way to actions can be learned completely, unsupervised. Now, is this unsupervised? You query the simulation millions and millions of times. And the interesting thing is the following. They say, oh, Q-learning is model-free. You don't need to build a model. But if you query billions of times the simulator, and the simulator is the model, is this really a model-free approach? I mean, you query the model all the time. You ask it questions, all right? So you assume you know it. And that's why these things work on simulated environments. So now we'll discuss about Go a little bit. Are there any questions so far? I can explain this a little bit with the model-free. Model-free approaches do not try to learn a model of the world, and usually they work on simulation where it is effortlessly, you can ask the simulator to tell you what's going to happen if I do this. You can try all crazy actions you want. You can crash and die as many times as you want. Unfortunately, in the real world, you would never want to do that. You always want to be safe. You always want the robot not to crash, okay, because they're still very expensive. And it's very hard to, transfer those approaches into the real world, okay, because of their sample complexity, safety concerns, etc. Now let's see Go. Well, everybody knows that DeepMind developed a program called AlphaGo, which beat the world champion Lee Sedol on Go. Go is an ancient Chinese game. Let me explain. There is this board. The board comes in different sizes. Smaller sizes are easier, right? They're 4 states. They're easier to tackle. These are called stones. And the person that wins is the ones that has conquered most of the territory on the board. All right? It's a very difficult game because there are way, way more states, both than backgammon and chess. However, DeepMind was able to do very, very well using the following strategy. Given a configuration of the board game, they learned 2 mappings using 2 neural networks. One learned to map the board configuration into an action, probability of the next actions, and the other learned to map the board configuration to a probability of success. The first one was trained from expert moves. Okay, very simple. The second one was trained to predict the outcome using safe play data. Now, when you should play, you need to play with some certain policy, and here they use the expert policy to play, I guess, that they learn from expert moves. Okay? At this time, both those networks will guide a search. The action will tell you which actions should you evaluate and which actions you should forget, and the evaluation will tell you how to prune the branches. Oh, you know what? This is a really bad configuration. Don't explore further from here. Okay? Now, they had to unfold the tree for quite long and quite many times. What allowed them to do this is a new hardware called tensor processing unit, which was developed by Google and was essentially trading precision for capacity. You were able to put more instructions per silicon on that chip. It was specifically developed for machine learning. And they say that it is equivalent to 3 generations of the Moore's law, 7 years fast forward of the technology. And all this thing was used to beat Lee Sedol, all his machine over here. Okay? So this is the hidden actor in the game. So let me just say that before that, people were using Monte Carlo tree search, essentially this tree unfolding, to play Go. But what DeepMind did is that it had these intelligent neural networks to learn to guide the search. So we learn now to search, okay? And now you're going to say, but since we have a policy, why don't I at this time look at my policy network and just predict whatever action it says? Well, the thing is, exactly because the state space is so huge, if you unfold forward in time, you will always do better because you'll be able to forecast the future, And keep in mind that here, this forecasting is correct because you will be querying the Go simulator. You know how the Go, environment works. Okay, so you will always do better if you look ahead as opposed to this baseline policy that you use to prune essentially your tree. Okay. Any questions? Yes.
How does this AlphaGo project model the other agents' actions during tree search?
Potentially, they say under all possible actions of the other agent, what shall I do? Like worst possible case for me.
So why we need two networks, not one network? For example, like we just have the value network and then the learn policy.
Yes, because then you have a huge branching factor, and value helps you to prune the trees, but it doesn't help you how to guide to pick the branches, which actions, some actions you may never need to even sample to evaluate. Otherwise, you need to open all of them and evaluate, and post-mortem evaluate and say, okay, I shouldn't have opened this one in the first place. I mean, if there are so many actions, okay, it is worthwhile to just query a few of them based on your actor network, as opposed to all of them, and then prune with a value network. Okay, so experts were used to train this policy network. We talked about the hidden actor here. Now, progress was made, and then DeepMind produced AlphaGo Zero. AlphaGo Zero didn't need anymore the human experts. And the big thing was the following. Monte Carlo research was not used at test time, but also at training time. This means that during self-play, I'm not going to randomly sample actions. I'm going to do a very informative search of what actions I'm going to explore. So each time you want to play against yourself, you're going to sit there and think for 0.4 seconds. Okay, so you're following many trees based on your current value and action networks and pick the right action. And it looks like this. You are in a current configuration, and then you open this Monte Carlo research based on your current policy and value networks, and pick an action very, very intelligently. Before, if you remember, you would just query your policy network. Now you don't. You just look ahead. And you use the policy network to do the look ahead, but you use the look ahead to propose the action. You take this action, you go next, you unfold. At some point, you see the end of the game, okay? And then you use this end of the game to go and inform your value network and policy network, okay? And other people say that another big change was the two networks, the value network and the policy network, were not two disjoint neural networks. Rather, we expect that it's going to be a lot of synergy and a lot of shared features. So essentially, you have one neural network with two heads. Okay, and this is standard practice now in multitask learning. So here, you play, and when you self-play, you are extremely intelligent of how you sample your actions. And I think that was a good question. I need to check how the action sampling was done in self-play for TD Gammon. For Monte Carlo research, the actions was based on learning from expert demonstrations. I'm going to double check for TD Gammon. And here, those actions are extremely, extremely well thought through. Okay? So fantastic, much better exploration, much better exploration. So let's see the result. The result is that those AlphaGo Zero was not very good at predicting expert moves, but was much better in winning the game. Okay? Was able to do better than human experts. Okay, and suggest different strategies. And depending on which side of the fence you are, you may be extremely excited or extremely upset. But let's go back to this important picture. This is not AlphaGo. This is a DeepMind person moving the stones on the board. So this suggests that beating the world champion is easier than moving the stones on the board. Okay, and let's see, since we solved AlphaGo, how can we go and, learn to act in the real world? What are the big differences? Okay. So first of all, the biggest difference is that for AlphaGo, the environment is known. While here in the physical world, for our agents, the environment is not known. They need to learn the model of the environment. Just to make sure, this model is used each time we call the Monte Carlo research, right? We say, do this action, and then the senior says, okay, I'm going to do it. Here is the new board configuration. Okay? You just place the stone where you want. Very simple model. All right? While in the real world, we need to learn how our actions influence the physical environment around us. Yes. The other thing is that the model doesn't change. That's it. Here is Go. I'm not even sure if how much transfer there is between the different sizes of the boards, but you just need to do fantastic on that environment and that's it. In the real world, constantly things are changing. Now, maybe something is going to be placed here, and I need to make sure I don't each time dump it and push my laptop off the chair, okay? So the environment changes, there are environmental variations. The actions, they're discrete versus the real world are continuous. They're just one goal, let's bit go. Well, here we have a large and diverse set of goals, even for very simple tasks. For example, to make pizza. There are so many other things you need to know to achieve this very simple goal. And the last very important thing is that when you're an agent acting in the world, you need to be able to assess whether your goal has been achieved. You need to be able to see, did I put the water in the glass or did I spill it all over? So you need to have fantastic computer vision ability. While in Go, the simulator tells you, lost or won. Let's see. Let's talk first about the first two. Learning the environment. Well, there is this very important task called state estimation. State estimation means you take the pixels and you try to infer where are the different objects, where are the important parts that influence my task, that I need to keep track of, okay? And you also need to, as we say, check whether you achieved your goal. Right now, in robotics, oftentimes we have instrumented environments and we have AR tags to say to the robot, yes, you managed to open the door. There are IMU sensors there. It's not that the robot is trying to open the door, but cannot figure out whether it opened the door or not, right? You have the IMU sensor to say, yes, you opened the door. This is extremely biologically implausible, okay? Usually, works on state estimation go between two extremes. The first extreme says the model is known, everything is known, the 3D meshes, their physical properties, inertia, friction, etc., locations, poses, everything. And I'm going to act on that environment, and I'm going to plan ahead, and there are fantastic planning algorithms developed from robotics research. And then there's another thing that says, you know what, I'm just going to take the picture, and just, without any intermediate supervision regarding where the objects are, how they look like, what is their motion, etc., I'm just only going to be supervised by my end task, which is predicting the steering angle, okay? Right now, people have started understanding that, we may need to do some intermediate supervision here regarding where the objects are, what are their motions, etc., which can be trained from different datasets and transferred to help learning to drive or learning to navigate or learning to do whatever. And we will talk about these approaches in the course. Now, the bottom line is that learning to act is difficult because understanding the world and how the world is very difficult, which is because computer vision is difficult. So all of you are pushed towards, that wonderful field of computer vision. Another thing I want to discuss is diverse versus continuous actions. There are more and more degrees of freedom, and the question is, how do you explore with that high degrees of freedom? There are solutions we'll discuss about curriculum learning. You start from few degrees of freedom and you add progressively more and more. And in fact, this is how baby hands work. In the beginning, they cannot do a lot of things, and as they some policies based on this very simple gripper, they start adding more and more figures. One goal versus many goals, we'll discuss about recent work that explores exactly what we mentioned in the beginning, the conditioning of the goal. So the policy is not just a mapping of observations to actions, like Go, but rather observations and goals to actions. And the most important question is how this goal is encoded. Is it an image? Is it some 3D configuration? Because if it's an image, how I'm going to, represent things that are hidden. For example, this inside the water inside the glass. The water is not visible, okay? So we will discuss about those encodings that are very, very important. And the last is, of course, rewards. We need to be able to build agents that can detect their own success, learning perceptual rewards, and there are also works that we'll talk about this. So let's go again to our favorite picture here. This has been realized by many people. The fact that, learning goals is probably easier than, acting in the world. And there is Hans Moberg, who is in fact an adjunct professor here in CMU, that stated the AI's paradox. The fact that it's easy to make computers to exhibit adult performance on intelligent tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old, okay, on perception and mobility. And do you agree with this? Isn't this amazing? And state on the words of Marvin Minsky, we're more aware of simple processes that don't work. For example, oh, I don't think I solved this math problem well. And we are not aware of super complex ones that work super well, like my ability to distinguish all of your faces right now. Okay? Now, this is the AI's paradox. But the most interesting is the solution that Moravec, the explanation that Moravec proposed, why this is the case. Now, before I show you that explanation, which we are not sure if this is a correct answer, but I'm extremely excited about, why do you think this is the case? Why this is so much harder than, yes?
So I'm wondering, so here it means that the perception as 1-year-old boy is simple, right? Simpler than years ago, for example. So,
I'm not that sure, because let me explain. Even just perception of some objects moving around, even this we cannot do very well, right?
so my question is that, does that mean that we do not understand the perception well?
So the perception is one part, and the manipulation is the other part. How do you pick up this particular stone? Both the perception as well as the motor skill, together. Visual motor, all the visual motor skills are difficult.
Is that a case that we learn the rule of go well, but not learn the rule of perception well?
Yes. And it's not clear that we can distill perception into, let's say, a small set of rules. Yes.
So for the, say, AlphaGo, like it works very well when we have a binary reward, like we win or we lose. Does it work well for when you have a continuous reward? I say we have a number indicating your successful level.
Yes, in fact, I would say that this is even more informative reward. If for every intermediate board game you say, okay, this is good for 0.7 probability, even teacher supervision if you had these oracle numbers. Yes?
So you asked for an opinion on the AI paradox.
Yes, that's what I asked.
Is it like the simple processes all go through conscious thought, which is kind of like suited for a big variety of tasks that are simpler, whereas the complex ones are kind of hard-coded and very subconscious? That's what it is.
So one second, which ones are subconscious?
Like the complex ones that we don't really think about, like walking and recognizing.
Yes, it is subconscious. We're not even conscious that we're looking and we're recognizing everything, right? While when we're solving a problem, we're very conscious and struggle towards it, right? Yes, so why is this the case? Yes.
It's because those tasks like control have been evolved over many, many generations of humans. We don't even have to learn them.
Exactly. That's exactly what he suggested. I think it's fantastic. It's just a matter of training. We had hundreds and thousands of years to perfection our perception and motor skills, to survive from the wild animals. Potentially, 66 million years ago, when the first human species came out, they had huge difficulty running away from the lion, right? But then it became better and better. And they had huge difficulty on distinguishing potentially the animal behind the bushes. But this also evolved. So we had so much time to evolve. So the explanation he proposes is based on evolution. Okay? No magic here. So then, what he says is that the difficulty of, he calls it reverse engineering, you can understand that it's as learning, okay? The difficulty of learning any human skill is proportional to the amount that it has been evolving in animals. We have spent few hundreds years doing cognitive abilities, okay? So potentially we are not as much fine-tuned on those tasks as we are on visual motor, basic visual motor skills, okay? And exactly, the oldest human skills were so, how to say, perfect, that we don't need even to be conscious and spend attention there. Of course, once you see, this night and you don't see well, you say, oh man, I really need to focus now, right? But most of the time, you don't need to focus. So, those that effortless skills for humans are going to be difficult for AI to solve, and those that are difficult for us, they should be easy for AI to solve. That's why, and here's another wonderful gentleman that says, what is AI? What is artificial intelligence? We need to do things the way people do. But what are the big milestones? And he says, the big milestones is to achieve it used to be, remember, to be thought that the difficult things to achieve is what highly educated male scientists found challenging. Chess, involving integration, proving mathematical theorems, etc. However, what children do, nobody paid attention. But they can distinguish the coffee from the chair, they can walk around in 2 legs, find their way, okay? And what he said, and he's a professor in MIT as well as an entrepreneur behind many robotics companies, he says, no cognition, forget about it. Just sensing and action. This is what we need to learn. We need to learn to make rats, excellent rats that can adapt to dynamic environments, okay? With the cognitive abilities, they're going to come later, okay? And they're not that difficult. You just unfold the graph and you put also 2 neural nets to prune well, and potentially that's it. Okay, so this is extreme. I'm not saying that these are open questions. We don't have answers, okay? But it seems to me that babies, we have a lot of things to learn from them. And there is this wonderful paper of how babies learn, okay? These are the 6 lessons that the 2 psychologists suggest as important for learning behaviors. Be multimodal, use multiple sensory input, this means. Be incremental, don't try to teach the very difficult thing before teaching the very simple thing first, so that you can build on it later. Be physical, let it interact with the world. Explore, this is extremely important, intelligent exploration, and this we're going to talk a lot in the course, and you will have a chance to unfold your creativity during the final project. Be sociable and learn the language, so that you are able to communicate with humans and get supervised by them. Do you have any questions on this last part of the talk? Okay, so I'm kind of done. There are 10 minutes, and I'm going to let Professor Tom Mitchell take it from here and tell us his opinions.
Let me turn this on so. Hi. So I'm Tom Mitchell. I'm going to be the other co-instructor with Katerina in the class. And we thought we would try something a little different, which is each of us promises to the other that we're going to end lecture a few minutes early so the other person can riff on whatever we said. So forgive me, but this is a real-time experiment on whether that will work or not. So let's see. First of all, I think I want to say that there were many wonderful and illuminating things Katerina mentioned, but for me, the most valuable lesson was that the sea animals eat their brains. And so I encourage you to remain very physically active throughout the semester. I also have to say I was reminded during this lecture, something I didn't even tell Katerina, but my very first machine learning class that I took, it wasn't really quite a machine learning class, but when I was a student, I took this course from a wonderful guy named Bernie Woodrow, and we had to do a course project. And I ended up actually doing, this lecture made me remember, my course project was to write a computer program that played games against itself to learn to play 3-dimensional tic-tac-toe. So it's a very simple game, but in fact it learned an evaluation function, and it had 2 steps. It took a move and let the opponent, which was itself, take a move. And I was very proud that by the end of the semester it could beat me at 3-dimensional tic-tac-toe, which was maybe a low bar to pass. But I think that in this course, the projects are going to be a real opportunity for you to explore not only the kind of textbook content that we're going to be teaching, you really want to learn the current state of the art of reinforcement learning, but there are also going to be an opportunity for you to push a little bit further and to experiment with some ideas that maybe currently in the state of the art. And so I just want to end by mentioning a couple of themes. I thought Katerina did a great job of showing us some examples of reinforcement learning, and then pointing out how, for example, the AlphaGo example is kind of a special case in some senses. And what are the dimensions along which we could broaden? For example, it's a special case in the sense that we know the rules of the game. We know the next state function. And so we can do a perfect simulation of the game. Whereas, for example, if you're trying to use similar reinforcement learning techniques to train a car to drive on Pittsburgh city streets, we don't really have such a perfect simulator. And so there's an example of a kind of dimension of the problem where there's very active research in which you might decide to zero in on your own project, for example. So I just want to mention a few others. To me, one interesting dimension is really sharing across different agents. So you saw the movie of the team of robots at Google who were all trying to learn. But there's an interesting question that's really kind of open about what should one robot tell to the other if they're all working together on this. It's not completely obvious. Because they're robots, they have the option of doing a complete brain transplant into the other robot. But of course, that would erase from the other robot anything it had learned. So the question is, what's really the right way to take, let's say, the learned neural network of robot A and the learned neural network of robot B, put those together. So that's, I think, another dimension of reinforcement learning which is very open. Another dimension is advice taking. If you're an expert at playing some video game and you're out with your friend and they're playing the video game, you might stand behind their shoulder and say, oh, no, go left here because there's a zombie over on the right. How do we get computer programs to take that kind of advice at the same natural language advice, perhaps, or even demonstration and natural language kind of advice together with doing look-ahead search and experimenting in the world? So that's another direction which I think could be interesting to explore here. So anyway, those are just a couple. There are many more. And as the course goes on, we'll be looking more mathematically at many of these algorithms. But I want you to think of the course, I think of the course, as a kind of two-thread activity. One is make sure by the end of the course we all really understand the current algorithms, the state-of-the-art, the set of ideas that the community has developed. But also, the other thread, let's challenge ourselves to push the state-of-the-art and use these projects, which will be a substantial part of the work that you do in the course, to really advance the state-of-the-art. Okay, the other thing we agreed on is that we're going to end on time. So I'll end there. That leaves us the time for a few minutes of questions if people have them, or we can end here. Okay, you're voting with your feet. We'll take that.